Thank you for stopping by my series 10-minute astrophysics, or it's about 10-ish minutes, maybe even 15 if we get really deep into it. But I'm just going to be reading from a lovely book by someone named Becky Smethurst. She has a YouTube channel that I'm going to tag below, and this book is called Space, 10 Things You Should Know. And it's a really good book. I really love it. So this is the second chapter that I'm going to be reading to you. And it's a really cool chapter. It's called In the Beginning There Was Nothing. So very cool. And we're just going to jump on into it. If you like this story, please check out her channel. Please give me a thumbs up and maybe even a subscribe. I just like making these videos for fun. So yeah, thanks for stopping by. Let's get into it. We've got to start hydrating, you know? And I love these like recyclable water bottles or made from recycled material. Anyways, let's get into it. In the beginning, there was nothing. All right. So the human brain cannot truly comprehend what nothing is, right? By simply thinking nothing, we turn it into something. So when we say that there was truly nothing before the Big Bang, it's hard for the brain to understand what that means. The concept of a before also doesn't exist without the Big Bang, as time itself was created in it. Even space didn't exist before the Big Bang, so there was nowhere and that nothing could be found. All the energy and the matter in the universe was produced in the Big Bang. And as a single human being, we are just one infinitesimal, that's such a hard word for me, infinitesimal chunk of that energy budget. Energy cannot be created or destroyed according to the first law of thermodynamics. So we are really only working with what the Big Bang gave us. There's no mythical energy tree in the galactic back garden we can go out to and shake when we have need for it, you know? The story of how we know the Big Bang happened is perhaps one of my favorites in the history of astronomy. Overnight, the edge of the entire known universe went from the furthest star at about 100,000 light years away to containing whole other islands of billions of stars, trillions of light years away. I would have loved to have lived through that time, a time when as one humanity's entire worldview changed. Akin to the European explorers standing at the helm of their ships on the shores of America, when they came to the shores of America, my apologies, 500 years ago, when their known world was suddenly catapulted forward, but on the biggest scale you can imagine, a scale that even now our brains struggle to comprehend. That's true. I can't imagine, like trying to imagine what life was like before there was such a thing as time and space is really hard for me. I don't know about y'all, but that's just not something that I'm a pretty, imaginative person, but it's just hard for me to imagine all that. Okay. One thing we must first establish, however, is that the Big Bang was neither big nor a bang. Crazy. The name was coined as a slur against the newly emerging hypothesis of an expanding universe back in the 1930s, and it's been plaguing astronomers ever since. The breakthrough came from a chap called Edwin Hubble in 1929, building on the work of Shapley, Curtis, and Opic earlier in the decade. Probably not something he ever expected to do after focusing mostly on sports in his early life and then training as a lawyer. But after turning his attention to his passion for astronomy, he took a position at an observatory in California. And it was there that he observed that what at the time was referred to as spiral nebula. A nebula back then was basically anything in the sky that wasn't clearly a star. They were the fuzzy, dusty things that umbrellaed everything from star-forming regions in our own galaxy to remnants of stars that had gone supernova and, unbeknownst at the time, galaxies of billions of stars. Wow. Hubble was trying to work out the distance between these spatial nebulae using stars that pulsated and changing their brightness. These stars are called Cepheid variables and were intensely studied in the Milky Way by Henrietta Leavitt in the early 20th century. She discovered how often the star's pulse was related to how bright they are, something we now call the Leavitt law. The faster a star pulses, the brighter it shines. When Hubble spotted these pulsating stars in the Spiral Nebula, he needed to understand how fast they pulsed in order to know how bright they were. And then from how bright they appeared, he would know how distant the star was. This is the same thing that you do when you cross a road at night. Based on how bright a car's headlights appear, you can tell how far away it is. From this, Hubble found that the Cepheid variables in the Spiral Nebulae, or nebula, multiple, I don't know how you say it, were more distant than anyone had ever considered, meaning the sizes of these spiral nebula were as big as the Milky Way itself. What Hubble actually observed were galaxies. Never has there been another result in which there was a bigger impact on astronomy. In one fell swoop, Hubble paved the way for an uncountable number of fields of research and changed our view of our place in the universe. But Hubble didn't stop there, though. He also took what's called a spectrum of each galaxy. This is where you split light through a prism and look for traces left by different elements in the rainbow colors produced. Wow, that's embarrassing. If you're picturing Pink Floyd's The Dark Side of the Moon album cover, then you're right on track. I'll show you what that looks like. These traces left by different elements are a quantum physics fingerprint of sorts. Always the same color, i.e. wavelength, no matter what light is there. Sorry. I get a little giggly. What Hubble noticed was that these signatures all had their wavelengths shifted to redder colors, which meant that they were moving further away from Earth. Not only that, the more distant the galaxy was from Earth, the faster it was moving away from us. It was only natural to think that if everything is moving away from us, then at some point everything was much closer. Keep rewinding time and you'll eventually end up to a point where all the matter and all the energy in the universe is condensed into a single point. Thus, the idea of the Big Bang was born. The concept of an expanding universe is confusing to most people. For one, it gives us Earthlings a distorted sense of self-importance. All the things in the universe are moving away from us. We must therefore be in a great place of importance, surely. Well, no, it's all a matter of perspective. Imagine the playground game Cat's Cradle, where you wrap an elastic band around each hand and then you pull them apart to perform all types of dexterous rope-based tricks to your friends. You know what it is. If you were to look down at your hands, you would see that as you pull your hands apart, both ends of the elastics move outwards. Now picture how it might look to a tiny observer sitting on your left hand. They can see the right hand moving away from them, but they can't feel themselves moving any more than we can feel the earth beneath our feet moving around the sun spinning on its axis. Likewise, a tiny observer on the right hand would only see the left hand moving away from them. This analogy works equally well when you consider you haven't created anything new in the process. You have the same amount of elastic band you started with, it's just the band itself that's stretched. Similarly, galaxies aren't the ones moving, space itself is expanding. But here's the crucial bit, we're not creating more space as we do it. We are merely working with the space that the Big Bang gave us 13.8 billion years ago. But let's not dwell on the past. It's far more exciting to think what will happen in the future. Unfortunately, there will be no Hollywood-ized end to the universe. The first option is that we keep on accelerating in our expansion until there are such great distances between galaxies and stars that we are isolated in the vastness of the universe. The second, the Goldilocks universe, is more palatable. In this version, the expansion slows down until the universe reaches a happy medium, an equilibrium between the forces of gravity endlessly pulling towards pulling inwards, and the inexorable pull of expansion outwards. That was a tough sentence for me. The third option is at the Shakespearean tragedy end of the spectrum. Gravity ultimately wins the war against the expansion of space, and the universe starts contracting inwards until it reaches that tiny little point where all the energy that there ever is reeled back into a big crunch. Perhaps the universe has been doing this for eternity, cycling through big bangs and big crunches, with an odd waste product of carbon made in a supernova occasionally producing life intelligent enough to contemplate the endless cycle. Wow. So that was a great second chapter. And I'd just like to talk about the Goldilocks universe 1 second, because that's the universe that makes me feel the best, where there's an equilibrium between the forces of gravity and that's pulling inwards and the pull of expansion going outwards. A nice balance. I'd like to think that because in a lot of chemical reactions, you're looking for a balance and everything has its natural balance, you know? So I wonder if that's it. Or, like she said in the Shakespearean tragedy version, the natural balance is the cycle of a big bang and then a big crunch. A big bang and a big crunch, creating the side effect or the side product of carbon-based life forms, us, that can contemplate these, questions of how we exist and why we exist and where we came from. This has been a great time with y'all doing my 10-minute astronomy. I hope you understand the Goldilocks theory and all of the different things I talked about. If you have any questions, please leave them in the comments. I love you all so much. Please give me a thumbs up maybe, or a like, a subscribe, anything of that sort. I really appreciate every view. I love you all, and I